Okay.
Were you painting or something?
Yes, I was. Remember I told you I asked if anyone had painted? Didn't I ask? Didn't you? Right? I did. Yes, it was successful. It was actually, yeah, don't worry about it. It's good paint. It doesn't come off. I've taken 3 showers since I painted. Yeah, it doesn't come off. Yeah, yesterday in my class, they were like, "Sir, were you painting?" And I'm like, "I thought I got all the paint off my arms." They go, "No, look." And I was just like covered with paint. Here. Let's see here. I would show it to the whole class. Here. This is it.
Oh, wow.
Pretty good.
That looks nice.
So, I'm just showing off right now. Yeah? Yeah? Anyone else see it? Built by hand by me. Everything. Everything you see there. Fireplace, the stone, the cabinets, everything. Easy. Easy. So, everything. Yep. Yeah, I think I'm gonna. You don't have to act like you care, but I don't want to show just a few people. Yeah. So seriously, my idea here is as I get older and I start, I want to be able to do something on the side, not for money, but just to keep myself going. And I enjoy working with wood, so I'm gonna start building people cabinets. They pay so much money for crap like that, man. My aunt and uncle just had some custom built-ins put in. They paid like $7 grand or something like that, and mine look way better than theirs. You know?
Start making
Cribs?
People will buy that.
Custom cribs? Yeah. Well, once you work with wood, you can pretty much build whatever, right? So I'm just trying to build up my tool supply and get my wood shop in order. But anyway, okay. No, thank you. Okay, so here we go. What the heck? Oh no. Oh no. Maybe that's a sign. We should just cancel class. Yes. Don't make me feel bad. She told me I've checked over and over. She told me not to be there. So okay. All right, so look, last time we did the first part of 6.2, and now we're going to pick up with the second part. All right? So look at this first sentence. After we master the above concepts. Okay, so that's what we did last time. After you've mastered that, done all your homework, you understand, we can use that along with a new interesting type of substitution to do some rather complicated functions, integrate some complicated functions. These new types of substitutions are called trigonometric substitutions, which I will call trig sub. So we have now u sub, which is your basic, like, do you see something in its derivative, right? We have integration by parts, and then we have trig sub. And so don't confuse them. Because while we're doing problems today using trig sub, we will also be doing u sub within that problem. So we don't want to confuse the two, all right? Now, here's the general idea. And I can go through this and explain it, but I always like to do it, just write it out. So let's say that somewhere in our integral, okay, so I'm not going to put an integral symbol up here. I just want you to look at this expression. Let's say that somewhere within the integral we see that, okay? Square root of a squared minus x squared. Now, a here is a constant. So let me give you a specific example of this. Like, let's say somewhere in your root you saw 9 minus x squared, right? Then a is 3, right? And that looks like this, doesn't it? Okay, another example of this. This one's not so obvious, but I mean, it is the same thing. What would a be here? Square root of 2, right? Because that 2 there should be the a squared, so a there would be root 2. Understand? So as long as there's a constant minus the variable squared, we have this form. Would you agree with that? It's like a different square. Well, okay, so you might think, all right, split it into 2 because it's a difference of squares, right? You might be thinking that. So let's just see. If I were to split this into 2, it would be what? 3 minus x, 3 plus x, like that. The problem is if I were trying to integrate this, I still couldn't do anything with that. There's no like basic U substitution or integration by parts. Yes? You could go into two different routes. Yes. But you're still jammed up here because we know with a product you can't do them individually. So we still have some issues. So it turns out that even though we could do difference of squares, that's not the technique that we're going to go with. All right? We're going to make a very strange substitution. That's how we're going to do this. Pardon? A trig substitution. All right? So look at what I'm going to do. And just follow me out here. What I'm going to start with is I'm going to say let x be equal to a sine theta. And this is very strange. Because what I'm doing is I'm taking an expression over here where x is just x, right? And I'm saying I'd like to replace that x with this complicated looking thing, right? A sine theta. And you might initially be like, why make it more complicated? Like x is x, let's not make it worse, right? But it turns out that things are going to work out really nice if I make this substitution. So this is the actual trig sub that I'm making. Okay? I'm substituting a sine theta in for every x that I see. Now let's just take a look at what happens here. What would that turn into? What would the square root of a squared minus x squared become? It would become square root, now a squared is a squared, right? Minus, now what happens if I square x? It means I square this, right? So I square the a and I square the sine. Right? Now both of these terms have an a squared in them, right? So I'm going to factor out an a squared. And when you pull the a squared out, I hope that you see what just happens, or what's about to happen. Right? What is 1 minus sine squared theta? Cosine squared theta, right? That's why we do this, okay? So watch. This becomes square root of a squared cosine squared theta. And now you have multiplication, don't you? And because you have multiplication, we can take the root of each one. And the root of a is a. Oh, sorry, the root of a squared is a. The root of cosine squared is cosine. So we get a cosine theta. I told the class before, I know some of you got here on time, but I'm expecting an important phone call, and when it comes, I'm going to step out real quick, okay, just so you all know. All right, so look, if we have this expression inside of an integral, which could potentially be a problem, okay, like it'd be difficult to integrate, we could replace the x with a sine theta, and then this complicated expression just becomes a cosine theta. And that's why we spent last class doing trig integrals, because we shouldn't be too afraid of integrating a trig integral now, right? So things look pretty promising, would you say? Okay, now there's something else that we have to keep in mind, that if this were in an integral, right, we would have dx out here, wouldn't we? So we would need to know, like, if I switched this x over to something with theta, then what would I switch the dx over to? Because I've got to account for it. So all we have to do to figure out that is take this equation, our trigonometric substitution, and take the derivative on both sides. So the derivative on the left side would be, let me just draw an arrow here. So dx would be a what? Cosine theta, and then d theta. This is kind of like when we were doing u substitutions. We always had, you know, like du, and then we'd have dx over here. All right, so let me box up the most important things here. All right, if we see that expression, we can replace x with a sine theta. Anywhere we see an x, we could do that. This complicated root will always turn into a cosine theta, right? And the derivative of x, dx, will always turn into a cosine theta, d theta, and do not forget the d theta, all right? Make sense? And then from there, we look at what we have and we say, all right, can we do this or not? That's the trigonometric substitution. Now, this is the first trigonometric substitution. There's 3 of them. So we have to deal with what if this was a plus. If this was a plus, we have to use a different trigonometric substitution. And the reason why is because if this is a plus, and that's a plus, that's not a Pythagorean identity, right? A plus sine squared theta is not cosine squared theta. So we can't get this to work. So we have to use a different trigonometric substitution if this is a plus. Also, if these are flipped, if the order is flipped and it's x squared minus a squared, then we cannot do this either, all right? So that's kind of where we're headed, understand? So let's do an example with this one. By the way, on your formula sheets, right, that you're allowed to have on the tests, there is one sheet, it's in Canvas under course files, that has a summary of these trigonometric substitutions. So on the test, I'm not requiring you to memorize what the trigonometric substitutions are, and I'm not asking you to memorize like what they turn out to, you know, like these three things. I think they're all in the formula sheet, but do you have it there? Does anyone have it? It's not, they're like separate. There you go. So on top it says trigonometric integrals and substitutions. And on the bottom of that, you will see the three trigonometric substitutions. All right, let's do our first example. And where is it? I'm going to do a problem similar to this one. I don't want to do this one exactly. In fact, I think I'm going to take a gamble here and switch this problem up. And I hope I don't screw it up. Like, I hope I don't make it too difficult to integrate. We'll see. I'm going to go x to the fifth root. Let's change it to 4 minus x squared dx. All right, let's first remember that we would want to initially see if there's anything else we could do with it, right? Is there a basic U substitution? Is there integration by parts? You know what I'm saying? It turns out on this one, you might be able to get it with a basic U substitution. You might be able to get it with U is 4 minus x squared, and then start playing around with things. Because I'm showing you this as an example of trig sub, I'm not going to do it that way, all right? It might actually be easier that way, but this is just to show you the method, all right? And there will be problems that we do right after this one where you cannot use anything but trigonometric substitution. So, all right? So do you see a squared minus x squared? Yeah, okay. So what is a in this problem? It's 2, right? The a is 2. So when we see this in the integral, we need to tell ourselves, okay, a is 2, right? A is 2. And now let's make the trigonometric substitution. So here comes the trig sub that I'm making. I'm going to replace x with a sine theta, right? A sine theta. So that for us would be what? 2 sine theta, right? 2 sine theta. Now, automatically, we know from what I just showed you that the entire ugly root thing, if I were to work it all out, replace my x with 2 sine theta and square it and do all that and factor out and blah, 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 this will turn out to be what? A cosine theta, right? So 2 cosine theta. So if you need to, ask yourself that question, how does that happen? Remember, it's just replacing that x with this, squaring it, pulling a 4 out, using a Pythagorean identity. You don't need to do that on the test, okay? All you have to do is make the substitution and show what this turns into, all right? And then we have one more thing that we're going to have to replace, right? We're going to be able to replace this root with something. That x to the fifth will be able to be replaced with this, and then dx is replaced with what? So what was dx always? It's just the derivative of this, right? So 2 cosine theta d theta. And now at this point, we just rewrite the whole problem. Okay, here we go. This integral becomes the integral x to the fifth. X to the fifth power. Yeah, this is x, right? So I'm going to raise that to the fifth power. So I'm going to raise the 2 to the fifth and the sine to the fifth. So 2 to the fifth, you could actually figure out what 2 to the fifth is, right? I'm going to just write 2 to the fifth sine to the fifth theta. Okay. Hey, we have an odd power of sine, don't we? Okay. Any questions? That's just x to the fifth. What about this root thing? What does that root thing turn into? 2 cosine theta. And finally, what does dx turn into? 2 cosine theta d theta. All right. And we got a bunch of 2's in there, right? That's 2 to the 7th power, isn't it? Which I'm just going to take out of the integral. And then we have sine to the 5th theta, cosine squared theta, d theta. And now that should look like what we were doing last class, right? Okay. So how do we deal with a trigonometric integral that involves sine and cosine if one of them is odd? We factor out, right? Well, we pull out or pull, yeah, you know what I mean. We kind of bring out or peel off one sign here in this case because the sign is odd. And I just need to carry that 2 to the 7th with me this whole time. So 2 to the 7th out here, integral, I'm peeling off one of those signs. I'm leaving the cosine squared theta there. And then I've got my sine theta d theta out here. And now you get to do what? Make a u substitution, right? A u substitution here, we're going to let u be what? Cosine theta, right? And the reason we do that is because the derivative of this is sine, well, we're off by a negative, right? So we know there's the derivative of it. So du here is negative sine theta d theta. And we don't like the negative, so we go negative here and plus here. What else? I've got to change this sine to the 4th over to a cosine, right? So it's sine squared squared? Okay. So this becomes 2/7 integral. This is sine squared theta squared cosine squared theta sine theta d theta. So what I'm trying to do now, since in case you're not, well, if you did your homework, you should be following me. This right here is the derivative, right? And so I need everything over here to have cosine in it. So I'm trying to get cosines. And so sine squared, I'm now going to rewrite that as 1 minus cosine squared. And then we're going to have to square that, so we're going to have to expand it or FOIL it, however you want to say that. I still haven't made the substitution, right? I haven't replaced u. I kind of knew what I needed to do, and then now I'm going and cleaning it all up, getting it ready. Okay, 2 to the 7th power, integral. Well, I guess, you know what, I could replace u now, right? Yeah, okay, let's do that. It's going to be 1 minus u squared times u squared, and then negative du, right? And I'm just going to take that negative way out to the front of the integral. And now this is in terms of u, right? So we're not quite ready to integrate this, right? We have to expand this first. And then once we expand it and pass the u squared through, then we'll have a bunch of powers of u, and we can integrate. And I'm going to take this one all the way, all right? So this is negative 2 to the 7th. All right, when I expand that, I'm just going to write that up here. I get 1 minus 2u squared plus u to the 4th, right? That's what I would get. And then I have to pass a u squared through it. So it would become u squared minus 2u to the 4th plus u to the 6th. Yesterday, I went over this section with my Tuesday, Thursday class, and we were talking about these problems. I don't know how we got on this, but we were talking about making lasagna. I don't know what. It's because it's like just the amount of layers that we have here into the problem, right? We've got, I mean, think about this. We're now in terms of u, right? We started in terms of x. So we're going to have to get u back to theta and then theta back to x, right? At some point, our answer cannot be in terms of u. So we got like multiple layers here. They like the idea of lasagna. They were all hungry, I think. It was, yeah, it's an afternoon class. That's why we got food involved there. And then someone else said it's like an onion.
Oh.
And onions make you cry, right? So I was like, yeah, maybe it's more like an onion. Okay, here we go, antiderivative. So we've got negative 2 to the 7th. I'm taking the antiderivative, right? So antiderivative of u squared, that's a terrible squared there. Antiderivative of u squared is 1/3 u cubed. And then minus 2/5 u to the 5th. And then plus 1/7 u to the 7th. And then that's it, right? Plus c. You know, when I was using, just a second ago when we used the Pythagorean identity, we use the Pythagorean, in order to do this technique, you have to use the Pythagorean identity, right? It's essential. And then within this problem, I rewrote sine squared with 1 minus cosine squared, didn't I? When you're learning the Pythagorean identity in pre-cal, you can't truly appreciate that formula until you start getting into courses like this, because then you start seeing it used a lot. You're like, okay, I'm using that tool to simplify a problem here, right? Without that identity, we're kind of stuck. Yeah. All right, so yeah, that's it right there. Now, what's u? I forgot. Was it cosine theta? Okay, so now watch this. This is negative 2 to the 7th. I'm just going to leave this in brackets. This is 1/3 cosine cubed theta, right? That's what cubing cosine looks like. Minus 2/5 cosine to the 5th theta, and then plus 1/7 cosine to the 7th theta, and then plus c. Still not done because our original problem was in terms of x. Okay, so now a very important step. Are y'all with me up to this? Okay. At this point, in all these problems, you'll get to a point where you got everything back to thetas, right? And now you've got to go back to x's. Sometimes it's just a quick transition back to x. This problem, I believe, is going to be a quick transition. But later on, it won't be so quick, so we're going to kind of do something to get us back to x. So I like to do it for every problem, just because that is kind of a cookie cutter method you can use. So the idea is that I need to go from theta to x, right? So here's what I do. I go back and I look at the original trigonometric substitution. What was my original trigonometric substitution? X equals 2 sine theta, right? This is an equation that relates theta and x, right? It gives me a relationship between the two variables. So what I'm going to do is I'm going to solve this for sine theta. So I'm going to rewrite this as x over 2 is sine theta, like that. And then I'm going to do something that hopefully your pre-cal instructor and maybe your Cal 1 instructor stressed to you, this idea of what we call a reference triangle. So from this, I'm going to draw a picture. It's going to be a right triangle. And this right triangle is going to be basically constructed using that piece of information right there. If I say sine of theta is equal to x over 2, I'm saying that the adjacent over the hypotenuse is x over 2, right? So if I draw an angle here, theta, then the opposite sides here has to be x, and this side right here, the hypotenuse has to be 2. Do you agree that that triangle represents that equation, right? Now what's great about this is that if I have that triangle, now I can come up with any trig function off this. I can talk about cosine, I can talk about tangent, cotangent, secant, cosecant, right? As long as I have all three sides. Now I don't have all three sides. I have 2 of 3. But you can always get the third side of a right triangle, right? So I'm going to trust that you can solve for this side. And when you solve for it, I'm hoping you're going to recognize it. Do you recognize that? That's what the root thing is that we were looking for in the beginning, right, to use the substitution. A little side note here. When you do a reference triangle in the problem, because you'll have to do a reference triangle, when you do that, one of the sides of the triangle will always be the thing that you did the trig substitution on. It's always going to appear somewhere on the triangle. All right, so check this out. Can you look at that triangle and tell me what cosine of theta is? It's this over this, right? It's this over this. Yeah? Now, I told you that sometimes you can go back faster. like a shorter way? Let me just show you. Do you remember we wrote this down earlier? Do you remember that? Go back and look. When we did this substitution, we said, oh, if we make this substitution, then we know that that root turns into that, right? Yeah. Okay, if right here I have cosine theta already, don't I? And I could have just divided by 2. And that's the same thing as this, right? What I'm saying is that you don't always have cosines here. Sometimes these are tangents, or sometimes they're secants. And so you would have to do something like this to be able to get that. That make sense? Okay, so let's finish this up. It's going to look ridiculous, but okay. So I have negative 2 to the 7th. Now I have 1/3, and then now I'm cubing cosine. So that means I'm taking root 4 minus x squared over 2, and I'm cubing it, right? That's cosine cubed. Minus 2/5. And then I'm taking cosine, and that's that, and I'm raising it to the 5th. And then plus 1/7, and then I'm taking root 4 minus x squared over 2, and this time to the 7th power, closing my brackets and adding plus c. And that now is my antiderivative. Yeah. I'm going to clean it up just a little bit, okay? Just a little bit. We've got way too many constants in there to leave it like that. All right, yeah.
Oh my god, negative 2 to the 7th over 3.
You know what, let me do it here.
7th over 5. Plus 2 to the 7th over 7th.
Okay, so look at this. Just let's see if you can follow this step. All I'm going to do is pass the negative 2 to the 7th through first. That's there. This is going to become plus, right? If I have a 2 here and I multiply it times 2 to the 7th, 2 to the 8th is there. And then this becomes a minus. And then I have that 2 to the 7th, which comes up here. Understand that? That's just passing the negative 2 to the 7th through.
And you wouldn't just cancel the middle term, the 2's?
Cancel the 2's. Where are you talking about?
Like the denominator and the numerator?
Oh, I'm about to do that now. Yeah, that's my next step. So when I cube a fraction, right, I cube the top and bottom separately? Yes? Yeah. Okay, so this is going to become, let's see what happens here. If I cube the root, right, do you agree I could write that as 4 minus x squared to the 3/2? That's the same as cubing a square root, right? When I cube the 2, I get 2 cubed, but I have 2 to the 7th here. 2 to the 7th over 2 cubed is 2 to the 4th. Yeah or no? Yeah. Okay, so I have out here 2 to the 4th over 3, and it was still negative. I guess I should move my equal sign up. Okay, so the 3 didn't go anywhere. This became 2 cubed. 2 to the 7th over 2 cubed is 2 to the 4th. I still had the negative up here. Yeah? I'm saying yeah, meaning yes or no? Yes? Okay, and then this one's going to work the same way. This means this to the 5/2, right? And let's try and see if we can figure out what the number is going to be out front. I'm going to have a plus 2 to the 8th over 2 to the 5th, right? 2 to the 3rd, so 2 cubed over 5. And then 4 minus x squared to the 5/2. And then the last one stays negative. And look at this one, 2 to the 7th over 2 to the 7th. That's going to go away. So 1/7 minus 1/7, and then I have 4 minus x squared to the 7/2 plus c. There we go. That's it. If you took the derivative of this, you should get that. That's a pretty monstrous derivative, isn't it? Like the 3/2 comes out, right? All of this raised to the 1/2, right? Then times the derivative, what's inside? Negative 2x. Plus 5/2 comes out, subtract 1 from this, derivative of the inside. You do that for all of them, and then once you get that, you could do like a common factor out, and things would work out. I'm not going to go through it. All right. Well, that took, what, half an hour? Yes? I was looking at an old exam from a couple of years ago, and my exam 2 was 6 problems. That's what I had given on a past exam. So I would expect 5 to 6 problems on the next exam. Yeah, you can't get one wrong. Well, you can get them all wrong, but you don't want to get them wrong. You don't want to get them all wrong. You don't want to get one completely wrong. All right. Well, making lasagna. All right, so there's 2 other trigonometric substitutions. Like I said, if you see the square root, if you see the square root of a squared minus x squared, then what we're going to use is x is a sine theta. That's what we just did. We know that the root thing turns into a cosine theta, and we know that the derivative of x turns into a cosine theta d theta. Great, fine, wonderful. All right, what if the integrand has a plus between them instead of a minus? And by the way, with plus, we could do both ways, right? So this could be x squared plus a squared or a squared plus x squared. Doesn't matter with addition. So if we do that, then we use a different trig sub. We use x is a tan theta instead of a sine theta. And then this root here turns into a secant theta. Why is that? I wonder why that would be. Because you're doing square root of a squared plus, you're squaring that, right? So that's a squared tangent squared. And then you pull out an a squared. You're left with 1 plus tangent squared. And what's 1 plus tangent squared? Secant squared. And then you take the square root of each one and you get a secant theta. So that's why this happens. And then this, you have to take derivative of this. And derivative of a tan theta, a is a constant, comes for the ride, derivative of tangent theta, secant squared theta, d theta. So we're going to turn this ugly thing into things with secants and tangents in it. And that's why we did that in the previous section. Now, what if our integrand has x squared minus a squared? And I had a student ask me, well, wait a minute, isn't that the same as, like, couldn't we make it look like the previous one by just pulling a negative 1 out? And then that would change that to a squared minus x squared? Right? Like if I pass this back through, right, I would get that. But that looks like the trigonometric substitution from before. The problem is that negative 1 out here. You would have to be able to get it out of the root for this to be equivalent, and you can't take the root of a negative number. So you can't get this out of here. So you're not allowed to do this little tricky thing. It doesn't work. So that means for this, we have a completely different substitution, and the substitution is x equals a secant theta. And then this root thing turns into a tangent theta, and of course the derivative of this is a secant theta tangent theta d theta. So you got secants and tangents again. All right, those are the 3 trigonometric substitutions. So let's do this. Let's do this one right here. I want to do something different though. God. I'm so afraid to tweak these problems because if you tweak them a little bit, they can blow up in your face. Let's try it. If we run into a problem, you know what? Let's not. Let's not. Today is not the day to go out on a limb and try something new for me. Okay, here we go. Let's do that. I'm just going to change the 9 to a 16 because. So, you look at this, you say, is there a basic U substitution? Do I see something in its derivative? And you're like, not really. I don't see anything in its derivative. Integration by parts, nah, no thank you. No thank you. So, but I do see x squared plus a squared under a root, don't you? You see that? That means A would be what for us? 4. All right, so if we have that form of x squared plus a squared, what is the trigonometric substitution that we're going to do? We're going to do x is equal to a tan theta. So 4 tan theta. And by default, if I worked out all the stuff for this, I know that that's going to turn into
It's 4.
4 secant theta. So this is in your notes, this is in your book, and this is on the formula sheet that you can bring to class. I recommend you bring those from here on out. And then dx is going to be what? Just take the derivative of that, right? So 4 secant squared theta d theta. Okay, so in all these trig subproblems, we always want to get like the 3 things in order. We've got what x is, we've got what that ugly root's going to turn into, and we've got what the derivative is going to turn into. And then we go rewrite the problem, and we just hope for the best.
Man, I'm sorry, how'd you get from the third line to the fourth line?
I didn't. I went from the first line to the third line.
Oh, okay.
So I just took the derivative of this. Okay? That's how I'm going from here to here. This is just the result of, well, this is the result of why we make this substitution, because this ugly thing turns out to something nice. But you could verify it by just taking 4 tan theta, putting it right there, squaring it, factoring out 16, and identity. But you don't, some instructors want you to do that every time. Like, do this, then work it all out, come up with this. I'm telling you, look, you can just use the formula sheet so you don't have to go through that process.
So in the first x, it's going to be 16 tangent.
Yeah, so this is going to become 1 over. Now this x squared right there is that squared, right? So 16 tan squared theta. And it's in the denominator. And then times, now the root here, what's that root being replaced with? 4 secant theta. And then dx is 4 secant squared theta. Now I'm going to write it like this, 4 secant squared theta d theta. This 4 secant squared is up top, right? I'm writing it out to the side, but it really means that's up on top. And so it cancels, the 4's cancel, and then you get one of the factors of secant to cancel. And so you're left with your new integral, which is 1/16 secant theta over tangent squared theta d theta. And y'all understand where that 16 came from? Okay. The 1/16th, yep. You pull it out and it's in the denominator, so it comes out like a fraction. All right. Well, we did some homework with tangent and secant, right? But in class when we did tangent and secant, every time we did those, the tangent and secant were up on top. You didn't have anything like this where the tangent was on the bottom. So when you run into something like this, my recommendation is that you just try and turn everything back in terms of sine and cosine. Okay, so let me just rewrite this and let's just take a look at what it is. This is 1/16 integral. Secant is really 1 over cosine theta. And tangent squared is sine squared theta over cosine squared theta d theta. That's just me trying to get everything in terms of sine and cosine. And now, you know, fraction over fraction you can flip, right? So basically this becomes the cosine squared theta comes up here, the sine squared theta comes down here, right? That's no longer there. And one of the cosines cancels. So you get 1/16 integral, so what's still on top? Cosine theta, and what's on the bottom? Sine squared theta, and then d theta. Have you been carrying your d theta the whole time? You need to make sure that when you're writing this down, don't lose that thing. Okay. My wife hasn't called me. It's kind of strange. Well,
We can change sine squared theta to cosine.
you could change sine squared theta to what?
To the identity of the,
You could go 1 minus cosine squared theta, or you could also use power reducing, but we know if we did power reducing, it would create a 2 theta, wouldn't it? I agree you could do that.
du equals cosine.
Du equals cosine, then what's u going to be? Oh, so a basic substitution. Yeah, that's exactly what we do here. So don't overthink this. Go back, like when you get to this new integral, just kind of reset everything and say, okay, now can I get this with a basic substitution? If not, integration by parts. If not, is there an identity? But this is a basic substitution. If we let u be sine theta, right, then the derivative of that is cosine theta. So it's there, right? Now you can't do it the other way around. We can't let u be cosine because then derivative of sine is trapped in the denominator, right? So basic u sub, u is equal to sine theta, du is cosine theta d theta, and now we can rewrite the problem. 1/16 integral of what? 1 over u squared, right? 1 over u squared du. Everything works out perfect. There's no constant we have to multiply. So this is 1 over u squared du? Okay. I'm going to write it like that because I'm about to use the power rule anyway, right? And then I do my little power rule on that. And when I do it, I get an antiderivative of negative 1/16. That negative comes from the fact that when you add 1 to this, you still have negative 1, so you have to scale by 1 over negative 1. Power, it's all there, right? This becomes u to the negative 1 plus c. Remember, we started this whole game out learning how to do this, right? And look at where we are now. I mean, we're pretty far away from that now, right? Okay.
and just put u back.
Yeah, let's get u back. So u was sine, right? Okay, so check this out. This is, math. In math, we are really good. Like humans throughout history have been really good, in terms of mathematicians, at being super precise with a lot of. I mean, we are just like math. Oop, there it is. Okay, y'all see if y'all can't take that back all the way. I'm gonna mute my microphone. So for those of you who I was telling, it came back good, but not great. So, okay. All right, you ready? Did y'all take it all the way?
Yeah.
So I was telling you before I stepped out that mathematicians were really precise about things, but this is one place in math where our notation just sucks, okay? And that's where if I replace this u, if I replace this u with sine theta right now, you might think we're talking about arc sine, right? But that's not what it means. It means sine raised to the negative 1. So there are two notations that are just terrible. These are not the same thing. And that's just an unfortunate fallback or pitfall of our notation system in mathematics. This is the arc function, the inverse function, and this means the reciprocal. This just means 1 over sine. And that's where we are right now. This right here means sine to the negative 1. All right? So we've got negative 1/16, and then we had, I'll write it as, well, let me do this. 1 over u, how about that, plus c? I'll just write it as 1 over u, because that's what it means. And then I'll replace the u with sine. So this is 1 over sine theta plus c. And then I'll go and rewrite that as negative 1/16 cosecant theta plus c. Okay. Now what?
So for a triangle.
Yeah, let's do a triangle now. So we call these reference triangles. And where do we start with the reference triangle? What information do we use? X equals 4 tan theta is where we start. That was our original substitution. We divide by 4. And then we draw our triangle. Theta goes here. And tangent is opposite over adjacent. So that means my x has to go here, my 4 has to go here. And hey, voila, look what's over here. X squared plus 16. I told you that would show up somewhere, right? All right. Cosecant is the reciprocal of sine, right? That's what we have over there. So this becomes negative 1/16 root x squared plus 16. That's hypotenuse over opposite, which is x plus c. There we go. That's it. Okay, now, for this, I actually kind of want to check to see if that is actually the antiderivative. The last one I said, you know, if you took the derivative, you would get that, right? And I didn't do it because I knew it was going to be too long and involved. But this one, I think I'm willing to attack. All right? So I'm going to take derivative of this. I'm going to go kind of fast, but you ready? Okay, so watch. I'm going to have negative 1/16 as a constant. It's going to come for the ride. And then I'm going to have whatever I do here. And this is quotient rule, isn't it? So I do derivative of the top first. Derivative of the top is 1 over 2 roots of x squared plus 16. And then times the derivative of what's inside. 2x, I'm going to put that right here, right? Times, that's the derivative of the top, right? Times the bottom. So that's squared and the 2's cancel. Okay, I know I'm going really quick there, but that's what the derivative of the top times the bottom is. Minus derivative of the bottom times the top. All of this over the bottom squared. All right? Now, I could get a common denominator between these two, right? This one I just leave alone. This one I'd have to multiply the top and bottom by the root, wouldn't I? So if I multiply the bottom by the root, I get this. I multiply the top by the root goes away, right? So now I can put these together. I'll do x squared, I'll subtract x squared, and then I'll also subtract 16. So what does that give me? Negative 16? So look, I got negative 1/16 out front. I'm going to have a negative 16 on the top over my common denominator, and then over x squared, but I could look at x squared as x squared over 1, so then I could flip it like this, and then the x squared would join here, and then this 16 and negative 16 would cancel, and I get 1 over, that's it. So remarkably, that is the antiderivative. Okay. Interesting. What do y'all think? Y'all like making lasagna? Let's do another one. We're doing this one. Buckle up. Here we go. This one is so this problem right here is a nice one.
Remember how in Cal 1 there's like a section where you use natural log to deconstruct super complex derivatives?
Mm-hmm.
Is there like an integral version of that? You can kind of like break things apart?
In some way, yes. You could put a log out here to be able to use properties of logs and then bring powers down. The problem with that is you would also have to have an e in front of it. So you could always put like you could rewrite x as e to the natural log x, right? So I could rewrite this whole expression as e to the natural log of that. And then the natural log of this stuff can simplify. But then you've got e to all of those things. And that becomes harder to integrate. So it's not an equation. In calculus, when we were doing limits, what we did is we could take like, it was easy to do a limit. When you had e to something, you could like figure out what's happening as x goes to infinity. Here we're not letting x go to infinity. We're trying to integrate a function. So when we get that e to the something, we have to be able to integrate it. And that we won't be able to do. So we'll be stuck. All right, so does this look like any of the forms that we have? Well, we have to rewrite the denominator to look like square root of 4x squared plus 9 cubed, right? That's first. That's what it means to raise it to the 3/2. And then, does that look like any of the forms? The forms we have were this one, and this one. And please note that on all of these forms, the coefficient in front of x is 1, right? And so that doesn't quite look like it because of that 4, right? But that's okay because we're just going to factor the 4 out. What do I mean by that? What do I mean by that? I'm going to come here. I'm going to factor out a 4, which gives me x squared plus 9/4. And then all of that cubed dx. Right? You can pull a 4 out of a 9. You just have to rewrite it as 9/4. That way when the 4 comes through, the 4's cancel and you get 9 back, right? And then what can I do with that root 4 times this? Can't I do these roots separately? So I can do square root of 4, and then separate from that, the square root of that. And what is the square root of 4? 2. So that becomes integral x cubed. I've got all this stuff cubed here, dx. I've got, you said that the 4 could be split off, so I've got a 2 here, and then I still have the root on the other thing. Right? That's that root 4 being split off and taking the root. And then I have cubed, right, on multiplication, so can't I cube the 2 and cube the root? And when I cube the 2, I get 8, and then I can pop that out. 1/8 integral x cubed over root x squared